I'm right. I took about I'll definitely try to take less than an hour.
Okay.
So is that reasonable?
Yeah, that's fine. You take an hour, I think.
Let's go ahead and start.
Okay, let's get started. Looks like Bjorn is announcing something well in advance here, but before he does that, let me announce that this is his last talk on Hilbert's 10th problem over subrings of Q.
Okay, so on behalf of all the organizers, I'd like to thank the other speakers. So, I think we're really lucky to have such experts here who could take time out of their busy schedules and deliver such excellent lectures. Okay, so I'd like to start with an advertisement for a semester-long program at MSRI in Berkeley that I'm organizing with a group of other people. So, and it's in general, it's going to be on rational points on varieties, but in particular, there will be a component of this semester that will deal with undecidability questions for things like Hilbert's 10th problem over the rational numbers. So, just for your advanced planning. So, all right. So today I'm going to talk about Hilbert's 10th problem over subrings of Q. So first, I should describe what the subrings are. They're easy to describe. So in terms of the primes that are invertible in the subring. So let P be the set of primes. Then the subsets of the primes are in bijection with the subrings of the rational numbers. So explicitly, if you have a set of primes, you can look at the set of rational numbers that you get by adjoining all the inverses of these primes to the integers. So in other words, this is the set of rational numbers whose denominators factor whose denominators factor into products of primes from S. And this is a bijection. So the other way, if you're given a subring of Q, you can just look at the units of R and intersect that with the primes. So in other words, look at the primes such that 1 over P, it belongs to R. And that will recover you the set S. Okay, so I'll also want to, okay, so now the question is we're going to look at these rings and ask which ones can we answer Hilbert's 10th problem for. And to measure how far we get, I want to have a notion of density for a set of primes. So I'm going to be using natural density, so let me define this. So if T is any subset of the prime numbers, then the natural density of T is defined by the following limit, which might not exist, but so the density might not exist, but if this limit exists, then that will be the definition of density. So first, you look at all the primes up to x. So count, and you ask what fraction of those belong to the set T. So that this ratio is the fraction. And then you look at what happens to this fraction as x goes to infinity. Okay, so that's the definition of natural density. And okay, so now what do we know about Hilbert's 10th problem? So let me make a chart here where I have the subring and the set S, the set of primes that it corresponds to, and then the answer to Hilbert's 10th problem. So at the bottom I have the integers, so that corresponds to inverting no primes. And we know by Matthias averages and so on that that Hilbert's tenth problem has a negative answer. And at the top of the rational numbers, that's where you invert everything, all the primes. And there we don't know the answer. So just below here, if you invert all but one prime p, then you get the ring Z localized at the prime p. In other words, it's the subring of Q of rational numbers whose denominator is not divisible by p. And Julia Robinson proved that, well, maybe not explicitly, but it's implicit in her work, that this is Diophantine as a subset of Q. And using that, you can show that whatever the answer is for Q, you're going to get the same answer for this subring. And in fact, the same will hold for if you take any cofinite subset of P. In other words, you take the complement of a finite set. So that'll just be an intersection of a finite number of these rings. And again, these will all have the same answer, just we don't know what it is. And it also follows from this fact that Z localized at P is definable. Is Diophantine in Q. That if you go up a little bit from Z, so if you if you take a finite set of primes and adjoin those, so then inside this ring you can show that Z is Diophantine, because you can have a Diophantine definition of what it means to be integral at a fixed prime. So you can reduce the Hilbert's tenth problem. Using the negative answer for Z, it immediately follows you get a negative answer for these rings. Okay, so now the question is, how far up can you carry these no's? So until recently, there were no results beyond these. So what I want to explain now is that for certain subsets of density 1, so you can give sometimes. So for some such subsets of density 1. Now density 1, so that means like 100% of the primes, but that doesn't mean all of them. It means that whatever's left over could still be an infinite complement. Because if you have a very sparse set of primes, the density could still be 0. And so its complement could still have density 1. Okay, so let me make more precise exactly what rings I'm talking about. Which sets of density 1 will be allowed. All right, so here's the theorem. Okay, so this is due to me, is from last November. So that there exists. Okay, so here's a precise statement. So there exist disjoint recursive subsets of the primes. I'll call them T1 and T2. Such that if you have any S that contains T1 and avoids T2, so in other words, such that if T1 is contained in S, but S is contained in the complement of T2, and then you form the ring whose the subring of Q corresponding to a set S, in other words, you invert the primes in S. Then the following hold. So first of all, there exists an affine curve I'll call E prime. So it will come from some E. So over R, such that if you take the Mazur conjecture, the analog of the Mazur conjecture for the ring R instead of for Q fails. So in other words, if you take the set of R points on E prime with coordinates in R and take the topological closure of that in the real points on R, then this has infinitely many connected components. So also, for these same subrings, so which can have, I forgot to say something important. I mean it's not like these are the empty set or anything. These are T1 and T2 are supposed to have density 0. So okay, of natural density 0. Yeah, so in other words, if you have T1 down here, and you force those density 0 set of primes to be in S, and you force a certain other density 0 set of primes to be outside S, but then anything else in between this density 0 set and the complement of T2, which is density 1, any set in between will be allowed as a set of denominators in here. Yeah, and of course T1 and T2, you want them to be disjoint so that so the statement won't be vacuous. Okay. All right, so let me finish the statement now. So there exists a Diophantine model of Z. Well, not over Q, but over this ring R, which can be close to Q. And then, once you have that, then it follows that Hilbert's 10th problem over the ring R has a negative answer. Okay, so I should say that this first part, this result, this was actually inspired by a paper of Schlappentalk, which just appeared this year. So so for part A, so see the paper by Alexandra Schlappentalk in International Math Research Notices 2003. So what she did in that paper is she proved an analogous statement for curves for varieties over rings that were subrings of higher number fields. Where she didn't quite get the same. It wasn't quite the same result. It was the result for one. Okay, it didn't apply to Q. It applied to certain other number of fields, and it got up to density 1 minus epsilon for any epsilon. Anyway, so she actually raised this as a question, whether you could do this for density 1 and whether you could do it for Q. So that's what got me thinking about it. Okay, so anyway, what I'm going to do for the rest of today is sketch the proof of this theorem. So it's a little bit involved. I mean, it uses a lot. I'm certainly not going to be able to present the whole proof, but just to say what some of the ideas are. Okay, so let me begin the proof. So it uses elliptic curves. So let me start with this elliptic curve. So this is over Q. Now, why did I pick this one? I could have actually, there are actually plenty of elliptic curves I could have used. The key property that I need that this elliptic curve satisfies is that if you look at the group of the Mordell of A group, in other words, the group of rational points, then this is of rank 1. Actually, I can tell you more precisely what this group is for this particular elliptic curve. I actually chose this elliptic curve to have some other properties that are sort of convenient, but not really necessary for the proof, that just help simplify the argument a little bit. So in fact, oops. So the Mordell of A group is isomorphic to Z. So it's, in other words, it's free group of rank 1 generated by 1 point. So I'll call P a generator. I don't remember exactly what. I think maybe the generator is 0, 1 or something. I'm not sure though. It doesn't really matter. Okay, and also the other convenient property that this elliptic curve has is that if you look at the real points, it has 1 component instead of 2. Remember, there are two different shapes that the real points of an elliptic curve can take, and so this is the case where it's just 1 component. And so as a Lie group, it's isomorphic to the real points, isomorphic to the circle group, real numbers modulo 1. Okay, so now the E prime will just be E without its point at infinity. I should say maybe that whenever I write an elliptic curve like this, what I really mean is that E is the projective closure of this, so it includes the point at infinity. And E prime is going to be the curve without the point at infinity. So E prime is an affine curve, point at infinity. Okay, so now the first step in the proof is something about the distribution of the prime multiples of the point P and how they sit topologically in the real points. So, okay, so the step 1 is looks at the set of L times P, where L is a prime number. And the claim is that this is dense in the group of points on the elliptic curve. So, okay, so why is this? So, well, I already said that E of the real points in the elliptic curve, that's isomorphic to the real numbers modulo Z. And now P is a point here of infinite order. So the number the real number modulo 1 that it corresponds to, if I choose a representative, that will have to be irrational. And so you can transfer, using this isomorphism, because this is an isomorphism of topological groups, you can transfer the question about the prime multiples of P being dense to the prime multiples of alpha being dense in the circle group. And fortunately, I didn't need to do any work for this because this is already, this corresponding fact on this side is already a theorem. It's a theorem from the 1930s of using analytic number theory. It's a theorem of Vinogradov. So it just says exactly what we want, namely that if you have an irrational real number, and you look at its prime multiples, then this has, if you look at the image of these multiples in R mod Z, then the image is dense. Okay. So that means if I choose my primes correctly, I can choose prime multiples of the generator that lie, well, with up to a little error. I can make them wherever I want to on the elliptic curve. So what I'm going to do is take, let's see, the points on the real points look something like, maybe something like that. So that this is the real points on the elliptic curve. And I'm going to choose a sequence of points, sequence of primes, such that their multiples have y coordinates approximately equal to the index of the prime. So this is going to have y coordinate about, so here, if here maybe this is the y equal 1 line. This is the y equal 2 line. So on. So okay, so let me write this. Exactly what I want. So here's step 2. So there exists a sequence of. So I can pick suitable primes. So a sequence, L1, so an increasing sequence of primes, such that if I take the y coordinate of the Lj multiple of P and look at it, then that should be close to J. So that should be an approximation to J. And in order for my proof to work, it will have to be less than or equal to 1 over 10 times J. Okay. The 10 is not so important, but anyway. So this should hold for all J greater than or equal to 1. Okay, so I can pick these primes because of step 1, because the prime multiples are dense, so I can make them so that their y coordinates satisfy this. Because the y coordinate map on E of R is surjects onto R. They're real points on the elliptic curve with all possible real y coordinates. Okay, so, and I didn't say, okay, there are going to be some extra conditions on these primes, but I'm not telling you what they are, because they're going to be needed in step 3. So that's what suitable means. Okay. All right, so in step 3, so in some sense this is a crucial step. So here's where we choose the sets T1 and T2. So choose the set T1. So remember, T1 is the set, well, I've erased the theorem, but this is going to be the set that's contained in S. So these are going to be the denominators that are going to be allowed in the ring. These are primes that are going to be allowed in the denominators. And so if you allow enough denominators, you can make it so that the points, the LJ, these particular multiples of P, such that the denominators of the coordinates of these points consist only of primes in T1. So you can make it so that these points belong to the have coordinates that belong to the ring R. Now, on the other hand, okay, here's the plan. I want to make it so that this set of points that have coordinates in R looks something like this, these points. So I want to, but at the same time, I don't want to have some garbage points coming in. Because if I get too many points, then I might have so many, if I have too much garbage coming in, then this set of R points on this might be even dense in the whole thing. Whereas I want to get some infinite discrete set in order to contradict the Mazur conjecture for R. So I need to also choose T2. So this is the function of this other set T2. By excluding certain primes from the denominators, I want to force most of the other points not to have coordinates in this ring. So, all right. So in particular, I want to make it so that almost no other multiples, besides the ones here, besides these particular prime multiples up to sign. So almost no other multiples of P are in this set of points that have coordinates in R. Okay, and of course, to satisfy the theorem also, you want T1, T2 to be disjoint, and also recursive. Such a disjoint, recursive. And of density 0, natural density 0. Okay, so this is actually the hardest part of the proof. So making a construction, sort of a recursive construction of these two sets of primes. So what goes into this proof is a study of the denominators of the coordinates of multiples of a point. So if you look at the sequence of, say, the denominators of the x coordinates of p and 2p, 3p, they satisfy a lot of nice properties. For example, you know how they grow. There's some Diophantine approximation results in height functions that tell you how the denominators grow. And there are also various results you can prove using formal groups about, for example, that if m divides n, then the denominator of the x coordinate of mp divides the denominator of the x coordinate of np. So things like, there are lots of results like this. In fact, some of these are probably going to come up when my students give their presentation because, they're going to use similar facts there. So you need facts like this, and you need even more, actually. You need to show that, maybe I don't want to go too far into this, and then for the density 0 results, you need to show that the T1 and T2 both have density 0 result, I use all sorts of other things like the theorem of Serre's theorem about the image of Galois group acting on the torsion points of the elliptic curve. So I'm going to skip all that. And so let's pretend I've finished step 3. Yeah, so it's in order to make step 3 work, you have to choose the sequence of primes, the L sub j's. You have to choose those carefully. Okay, but once you've done that work, then you get to the fun part. So, I guess it depends on your definition of fun. So then you can take the set of, let me give this a name, these y-coordinates. Let's call this y-coordinate y sub j. So y sub j is an approximation to the integer j. And so now I'll let A denote the set of all these y coordinates. And the claim is that this set, first of all, that it's Diophantine over R. And not only that, but you can make it into a Diophantine model of the non-negative integers. And OK, once you have a model for the non-negative integers, you can get a model for all integers as well. Oh, maybe I should have said, after you do step 3, after finishing step 3, you already would have finished part A of the theorem. Part A was the part saying that the Mazur conjecture over R was false. And the reason why is that this already contradicts the Mazur conjecture maybe I shouldn't call it the Mazur conjecture, since he never conjectured anything over these kinds of rings, but the analog of the Mazur conjecture for these kind of rings. Because what is E prime of R? Well, E prime of R consists of exactly these points and their reflections, their negatives, and maybe a finite amount of garbage. But even if you add in a finite amount of garbage, it's not going to affect the fact that you have an infinite discrete set, whose closure has infinitely many connected components. So OK, so that we're already done with part A. So this is step 4 is in the direction of part B, finding a Diophantine model of this. So this is over R. So to remember, let me remind you, what does it mean to have a Diophantine model? That means that you have OK, so let me say you need a bijection from these non-negative integers to A, such that the graphs of addition and multiplication on here correspond to Diophantine subsets here. Now, there's an obvious bijection between this set and this set. So, in fact, this set almost looks like it's just a little bit deformed copy of the non-negative integers. So the bijection is just going to be simply j goes to yj. So the inverse is just round to the nearest integer. And so, but now OK, well, it's not hard, but now I'm going to show that given any approximation to the non-negative integers of this type, and if the approximation looks like this, is this good? So it gets better and better as you go up. Then that will automatically be a Diophantine model. OK, so so this is the proof of step 4. So first of all, what is A? So as I was saying before, it's essentially if you take the set of R points on E prime, then you get these points, you get their negatives, which will be defined over the same ring. So so they'll be down here. It's like this be minus L1p, and so on, minus L2p. So if I take the y coordinates of all these points, so that's like projecting this Diophantine set onto onto one of the coordinates. Sort of by definition, this set will be OK. This is not equal. There's a dot here. I'm not sure if you can see it in the back, but maybe I'll make it a little bigger. OK, so this set is Diophantine over R, and well, first of all, I want to get rid of these negative multiples. So let me intersect this with the positive reals. This is probably the positive rational numbers, or non-negative. And the point is that this will still be Diophantine over R because you can interpret Q. You can interpret Q as fractions of numbers from R. And also, and then you can use Lagrange's theorem, which will say that that these numbers are the rational numbers that are the sum of 4 squares of rational numbers. So this intersection will be Diophantine, but it's still an approximation here because there's still the finite amount of garbage to deal with. These extra points, so there's almost no other by the way, maybe I didn't make this clear, but this means finitely many. That's what this is. Finitely many. There are finitely many exceptions that might come into here. So there might be some random point here that somehow snuck in, happened to have the right denominators in its coordinates. Okay, but that's finite. So, and if you change a set by a finite set, it doesn't change whether it's Diophantine or not. So you can just exclude those. So, yeah, so that's what this dot means. It means up to a finite set. Okay, so therefore, at least this set A is Diophantine over R. Okay, but that's not all we need. To show that it's a Diophantine model, we also need that the graphs of multiplication and addition here correspond to Diophantine subsets of A cubed. So let me now do this. Okay, so I'm just erasing the key inequality, but maybe I'll copy it over here. So what do we know about these elements of A? The thing we know is that the y sub j is close to j. In fact, the distance is less than or equal to 1 over 10j. So that's going to be needed. Okay, so all right, so now the claim is, so there are two claims. The first one is that the graph of addition is OK. In other words, the graph of addition on Z, so it's a subset of Z cubed, that corresponds to a Diophantine subset. So this is Diophantine over R, subset of A cubed. So how do you prove this? So, well, it comes from the fact that m plus n is equal to q if and only if the absolute value of is less than 3/10. Yeah, because each of these, y sub m is always within 1/10 of m, and same for these. So this number, this linear combination inside here is always within 3/10 of an integer. It's always within 3/10 of m plus n minus q. So the only way it's going to be less than or equal to 3/10 is if the integer within 3/10 of it is 0, which is saying this. And so that should be clear. And this gives you a Diophantine definition of the addition right away, because you just say that if you have 3 points in A, you want to tell whether the two of them add up to the third using this funny addition, which is like the round to the nearest integer addition. You just ask whether those 3 numbers satisfy the property that when you add 2 of them and subtract the third, it's almost 0. Namely, it's less than or equal to 3/10. And this, to say that a rational number is less than or equal to 3/10, that itself is Diophantine, because less than or equal to is a Diophantine relation, because you can define that in terms of the non-negative rational numbers, which we said you can use Lagrange's theorem for. Okay, so is there a question?
This is in R. You want to have this, what is this true in R?
The question was whether you have all these things true in the ring.
You're interpreting formulas in the ring R.
So I guess, well, you can, so these are supposed to be Diophantine definitions over R. So, I mean, but if you want to, you can also work with equations over Q, just because you can interpret Q as ratios of elements of R. I mean, you can, I guess, there's a little bit to show here. You have to show that, first of all, you can define the non-negative numbers of R so that you can make sense of fractions. But that you can do using similar tricks to what I defined in the first day. Remember the way I showed that you could define the non-zero integers by saying an integer is non-zero if and only if it's a product of something prime to 2 and something prime to 3. So you can use the same thing with R, because R also has 2 primes in it. The Dedekind ring R has at least 2 primes in it. So you can do the same thing. Actually, it's even known that if you have just 1 prime missing, you can still define not equal to 0. Okay, anyway, so yeah, so it doesn't matter if I can work with equations over Q or over R, because equations over Q can be translated into systems of equations over R. Okay, so any more questions? Oh. Well. Okay, so next I want to define multiplication. And this is what I did in my original proof, but Fedas pointed out to me when I lectured on this last 2 months ago, that you can simplify things by, instead of defining multiplication directly, you can first define the squaring operation. So it just simplifies the argument a little bit. So the graph of squaring, in other words, of the map m to m squared. So that's a subset of z squared, or non-negative integers squared. So that's, again, this corresponds to a Diophantine subset of a squared. And the proof is exactly the same as what it was for addition. You just have to say that, you just have to do an error analysis. Just say, so m squared is equal to q if and only if the absolute value of ym squared minus yq is small enough. And so 4/10 works. Because, well, this is something, at worst, this is like an error of plus, it's off by most 1/10m. And if you square this, and you just figure out how close this is to m squared, and you get three junk, well, okay, you get some junk terms here and junk terms here, so that's okay. So, and then once you have, so then once you have squaring and multiplication, once you have squaring and addition, then you can define multiplication using the relation. So everybody knows this. So you can, if you want to say what it means for m times n to equal q, you can just So I hope I got that right. Yeah? Okay. So that finishes the proof that this A is a Diophantine model of non-negative integers. So that finishes that's what part B of the theorem said. Now part C of the theorem said that Hilbert's 10th problem over R has a negative answer, and that all now follows from this Diophantine model, because, so now when you have a Diophantine model of the non-negative integers over R, and you also know that, and you also use the ingredient that Hilbert's 10th problem over Z has a negative answer. And you use this Diophantine model to encode this problem as a subproblem of Hilbert's 10th problem over R. And if you can't even solve the subproblem, that implies that you can't solve the general problem. So that okay. So this is the end of the proof. So maybe I'll just end with a few comments. So is there any hope of adapting this argument to get Hilbert's 10th problem over Q, negative answer for Hilbert's 10th problem over Q? So I kind of doubt it, but because it uses all these facts about denominators of points on elliptic curves, and it's not clear how to get anywhere unless you have a ring in which you can talk about denominators. On the other hand, you can also one thing you can do, on the other hand, is suppose instead of asking about subrings of Q, suppose you ask for subrings of higher number fields. Then the same proof, well, a similar proof would work, provided that you know an elliptic curve of rank 1 over that number field, K. Unfortunately, nobody knows how to construct elliptic curves of rank 1 over a given number field. I mean, for a particular number field, you might be able to do it, but nobody knows how to prove that for every number field, K, there exists an elliptic curve over K of rank 1. In fact, a priori, as far as we know, I mean, we know so little that there could even be some special number field K such that all the elliptic curves over that number field K have rank greater than 1,000. That might happen. I kind of doubt it, but nobody's been able to rule that out. So, yeah, so I think I'll end here. So thank you for your attention. So So the question was, what were the earlier results of Schlappentalk about proving Hilbert's 10th problem for rings of integers, but where infinitely many primes were inverted. So I guess she had a result in Invenciones about 5 years ago, maybe 5 or 10 years ago, where she proved that for certain number fields, not Q, but for higher number fields, for some special number fields K over Q, I think things like totally real or degree 2 extensions of totally real and things like this, she could find an infinite set of primes, so of density, let's see, I believe it was approximately, approximately 1 over 1, almost 1 minus the degree of K over Q, or something like this. And then for the rings of integers of K, where you invert this set of primes, she could prove the Hilbert's 10th problem. That Hilbert's 10th problem over such a ring had a negative answer. And the argument was that this ring, maybe I'll call the ring, so the trick was that this ring that she considered, the set of primes S was chosen so that when you intersect this with Q, you get just Z. So in other words, it was you choose the set of primes so that above each prime of Z, you're missing that one of the primes above each P in here is not in S, so that you get this intersection. And so then she gives a Diophantine definition of Z over this ring using this.
Other questions? Okay, let's thank Bjorn for that beautiful series of lectures. So it's 12 after 11, and I propose that we start again at 11:30.